Okay, good morning everyone. Welcome to our course Structural Theory. Now, today I will going to discuss to you one of the method in solving deflection or deformation for beams, frames, and trusses. Okay, it's called virtual work method or in the other books it is sometimes called unit load method. Okay, so we have two formulas here. So first, I'm going to discuss the formula for beam and frame. So as you can see, the formula is 1 dot or times delta is equal to the integration of small letter m times capital letter M over EI times dx, okay, from 0 to L. Okay, the virtual work method is going to be this way. So you need, uh, for example, you have a beam here, no, or a structure. So it is simply supported, and you know that we have a real loads. Okay, real loads. Okay, so if you cut it, no, if you cut the uh, beam, so you will uh, see the internal loadings, internal reaction. We have, as you all know, we have the shear and we have the moment. So M will be here, will be the internal moment. Okay, moment caused, okay, by the real loads. Okay, and then M will be, small letter m will be uh, this way. So if you, the same beam, so are you going to remove temporarily the real loads, so you will going to apply the virtual loads. Okay, if you are going to determine the deflection, okay, deflection at the mid span here, so you need to draw, okay, virtually draw a 1 unit load, okay, at the point where you're going to determine each deflection. Okay, so if you're going to solve for rotation or yung slope, okay, you need to apply rotation, which 1 unit moment. Okay, so let me clear that for you. So if you're going to solve for deflection, you're going to load a virtual 1 unit load, 1 kilonewton, 1 pound in English. And if you're going to solve for rotation, you need to apply a virtual unit moment, not a virtual load. Okay, if you're going to solve for the rotation at any point. Okay, so apply the unit loads. Okay, we have two loads here for deflection, vertical loads, and then for rotation, moment. Okay, 1 unit moment. Apply it in a point where you're going to solve for each deflection or each rotation. Okay, so M will be the internal virtual moment, okay, caused by the unit loads. Okay, so am I clear for that? So here on the denominator we have E. So as You all know E will be the modulus of elasticity, and I will be the moment of inertia, or these two, if combined, is called deflexural rigidity. So these two will prevent the deflections, or we will resist, okay, the deflections or the bending. Okay, so we have here on the right side a 1 kilonewton or 1 kilonewton per meter. So this is the virtual load. So 1 is the virtual load, okay, will represent the virtual load, and delta will represent the uh, external displacement, okay, due to real loads. Okay, so delta, uh, if we're talking about displacement, if we're going to talk about the rotation, so the formula will be like this, no? 1 times theta, the rotation, is equal to, the left side will be the same, right side, I'm sorry, will be the same. Okay? Okay, so 0 to L will be the limit, okay, where you are going to solve for the M and the capital letter M. So capital letter M will be in terms of the real loads, and small letter m will be in terms of x, no? Okay? Okay. So let's solve, let's use this formula in solving beam and frame. Okay? So let's go. We have here. So example, we have a beam here, uh, ACB. Okay, so ACB is uh, loaded by 8 kilonewton, uniformly distributed load, 8 kilonewton per meter. So we have the length of AB 4 meter and then 4 meter. Okay, so first, if you're going to solve for the deflection at C, okay, so first we need to again familiarize ourselves in the formula. So the formula, if we're going to solve for the deflection, so the required here will be the delta at the midspan of the beam, or at point C. Okay, so as you can see here, so there's two segment here, no? So we have the segment AC and the segment BC. Okay, first, to solve for this problem, so let's write the formula. Okay, at midspan or at point C is equal to, so we have two segments, so meaning we have to have the summation of m, integration m times m dx, okay, over ei. Okay, summation. Okay, so we need to add the two segments. Okay, first, let's determine the m. It's big letter M, okay, or capital letter M. Okay, so first, you need to solve for the reactions here. So solving this reaction, you all know that the AX at the pin is 0. So this is asymmetrical beam. So all you know that, as you all know, that the reaction will be equal, okay, at the supports. Okay, so 8 times 8 will be 64. right? So 64 divided by 2 will be 32 kilonewton at the left side and 32 kilonewton at the right side. Okay? And then after that, so we need to solve for M. So in this method, so you can start anywhere. Okay, so from for you to be for you to have an easier solution, so start from the left. If you're going to consider segment AC, no? Okay, so segment say AC to consider that. So you will cut this and assume that there's a positive internal moment here. So counterclockwise, if you're considering left portion, this portion, so positive counterclockwise will be the direction of our M. Okay, so using that one, this figure, so summation moment where you cut it, so this length will be X. Okay, 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 so you cut that. So emission moment at X is equal to 0 positive, we say counterclockwise, no? So M is positive, so counterclockwise will be the 8, no? 8 kilonewton is 1, no? 8 kilonewton times X times this moment arm, that's X over 2. And then we have the 32 minus 32 times X is equal to 0. Okay, so M here will be equal to 32x minus 4x squared. Okay? Okay, so we're going to use our virtual calculator here to solve that. Okay, and the next one, so we need to cut also the segment CB. So segment CB, same, okay, at x is equal to 0. So for you to have a simpler solution, so start from the left, from the point B, sorry, from the right to left, okay? So assume if you're going to consider right, so positive moment will be clockwise here, okay? So this is x, the summation moment at x is equal to 0, plus positive is clockwise. So m also will be positive here, okay? And then uh, plus 8 times x, okay? Times x over 2. Okay, so minus 32 times x is equal to 0. So m here will be the same class. So 32x minus 4x squared. Okay, so next thing to do is draw another a similar beam. So don't change the supports and the lengths. So here we're going to determine the deflection at C. So you're going to load the 1 unit load, the virtual 1 unit load at point C. Okay, so when 1 is at point C, we all know that the reactions here will be the half of 1, so zero point 0.5 kilonewton and zero point 0.5 kilonewton. Okay, we're using kilonewton because our given is in kilonewton. Okay, so 1 unit load. Okay, so the next step is you're going to cut same segment, okay, same number of segment and same directions. Okay, so if you cut AC, okay, make sure na the direction is from left to right. Okay, same with the capital letter M. Okay, so this one, so assume also small letter m, assume positive, so counterclockwise. Okay, so summation moment at x is equal to 0, positive counterclockwise. We have m, small letter m, and we have the minus zero point 0.5 times x is equal to 0. Our m here is equal to 0.5 x. So same with this. Okay, we start from the right going to the left. Okay, same here when we solve the capital letter M. Okay, so summation moment at x is equal to 0, positive clockwise. Okay, we assume that positive moment here, so clockwise, always assume positive moment. So M here will be positive, and then minus zero point 0.5 x is equal to 0, M is 0.5 x. Okay, so using this one, using the formula, we can now solve for the delta. Okay, so using the formula, so you can say 1 kilonewton, 1 delta C is equal to summation. So first, segment AB. So we consider the segment AB. So M of segment AB is 0.5 x times the M, so capital letter M, for segment AC is 32x, okay, 32x minus 4x squared, okay, over EI, okay, uh, don't forget the dx. Its limit is from, so its limits from A to C, so from 0 is your A, from to C that's 4, so 0 to 4 plus, okay, so next segment CB, so it's the same, okay, as you can see, okay, it's the same, 0, 4, okay, 0 to 4. So as you can see, we start at B to C, so that's 0 to 4. Okay, so delta here can be simplified, okay, can be simplified as 2 times 0, 4, 0 to 4, 5x, 32x, minus 4x squared, EI dx. So our answer here, using this calculator, we got that. So, okay, using this calculator class. So, stop again. Okay, so using our calculator here, so let's select that one. So, let me check. Okay, that one. So let's continue. So that is 0.5 x, right? Okay, it's 32 x, right? Okay, minus 4, okay, alpha x squared, no? Okay, Get 1. So limit here, the limit is from 0 to 4. So we forgot times 2 here, right? Okay, I think we are done. Okay, let's press equal. So the answer here will be, okay, our answer will be 1 to 80 over 3 EI. Okay, so positive. Okay, the answer is positive, meaning the direction of delta C is same with this unit load. Okay, so if the answer is negative, okay, if the answer is negative, meaning your delta will be opposite of the direction of the unit load you apply in the beam. Okay, so this one positive, so meaning your delta C is going downward, same direction at this 1 kilonewton. Okay, so as you can see, uh, 1 is uh, cancelled. Okay, so 1 kilonewton. So your answer will be here is in meter if you're going to substitute EI. Okay, so make sure of your units. Okay, if you use kilonewton meter in this uh, formula, so you need to convert EI in kilonewton meter. Okay, so for that, the 1 kilonewton will be cancelled out. Okay, so the answer here is 1 to 80 over 3 EI. So that's how you can solve deflection using virtual work method. Okay, the next one, class, is on frames.